Hello everyone, and welcome to the series on multivariable calculus. Today we're going to begin our exploration of higher dimensional calculus by first off starting to talk about how we can actually visualize surfaces in 3 dimensions or possibly even higher, and a couple different perspectives you can actually use to go about visualizing higher dimensional spaces. So as a guiding example, let's consider the three-dimensional surface characterized by the two-input function f of x and y is equal to sine of x plus e to the power of y. I've kept this function fairly simple. In particular, you can decompose this into a function of x and a function of y simply by addition. So the understanding of what's going on in the 3D realm for the surface is a little bit more easier to deal with. So let's actually focus on x, the variable, and let's actually treat y as a constant temporarily. So if we do that, what are we going to have? So if y is going to be a fixed constant, you can choose whichever constant you want, then what we pretty much have here is f of x some constant is equal to sine of x plus e to some constant. And since e is a constant too, that's just practically just another constant also. So what we have here is just vertical shifts. So vertical shifts of the sine function, sine of x. Now, in particular, as c tends to minus infinity, then we should know that e to the c should tend to 0 from the positive direction, right? And of course, as c goes to positive infinity, then e to the power of c is also going to go to positive infinity as well. So the vertical shift of sine is bounded below by 0 and not bounded above. So if we look at all of the different subsets of the surface from the two-dimensional perspective, what can we get? So we're going to have, the x-axis there, and what I'm going to put here is the f of x given some particular value of y, call that the c-axis. So here c is just a number, x is the variable of interest. So for example, when c is equal to or approaches minus infinity, what we have here is the typical sine curve. So this is c is equal to minus infinity. And then we have, for example, when c is equal to something very negative, so that's like e to the minus 100. So it's a positive number, but it's going to be very small. Then you're going to have a slight vertical shift of the sine function. So for example, you're going to have this purple curve. So this could be like c is equal to, I don't know, let's say -5, let's call it. And then, for example, we have c is equal to 0. That's actually an important one. So when c is equal to 0, that means this is shifted up 1. So if that point is equal to 1, then this curve is going to be c is equal to 1. Now, as c gets, c is equal to 0, sorry. Now, as c gets bigger than 0, then the distance, if you do incremental increases of c, for example, if this c is equal to 1, then the distance between c is equal to 1 and c is equal to 2 is actually going to be a little bit more bigger, because the gap is going to be exponentially increasing, right? So that's how pretty much we can visualize what's going on different two-dimensional perspectives of this three-dimensional surface. Now, what happens if we instead focus on the variable y for particular constant values of x? So if we think about from that perspective, for example, if we choose, for example, f of c, y, that's going to be equal to what? So that's going to be equal to the sine of c plus e to the value of y. Now keep in mind that sine of c belongs to the closed interval -1 to 1 for all values c for which you can choose in the set of real numbers. So what we're doing here is we're just increasing the value of e to the y at most by 1, or decreasing it by at most -1, or decreasing it by 1 in the opposite direction, right? So what do we sort of have here? So if that's the case, that means the exponential functions, depending on which angle you're looking at, so for example, if this is the y-axis and this is the f of c y-axis, where c is a particular constant. So for example, when c is equal to 0, you just have the original function. So for example, this is going to be equal to c is equal to 0. But also c is equal to 2 pi will generate the same exact value, right? So there's a bunch of different values of c, or a bunch of different values of x rather, that is going to generate that particular projection from the perspective of y and the vertical, what we're going to call as the axis. Now, of course, we can shift this down by 1, and then we can have, for example, this is going to be when sine of x is equal to 1, or sine of x is equal to minus 1, which is 3 pi over 2, so there's a bunch of different values that you could have there. And of course, you can shift it up by 1, right? So that's, for example, when c is equal to pi over 2, that's when sine of x is equal to 1. And there's, of course, infinitely many values that satisfy each of these different ones. And of course, you can have all of the values in between these two trajectories. Okay, so what can we sort of visualize from these two different perspectives? Because obviously the behavior along the x direction and along the z direction is very different. So how can we combine these two into, I guess, a sketch of the three-dimensional surface? So what we have here is that f is exponential in the y direction. That's characterized by those surfaces that I just drew. And f is periodic in the x direction. Those are those little sine waves that I drew up in this little graph with the orange, green, red, purple, and green. Therefore, from these two, we can say that f is an exponentially periodic surface. So what does an exponentially periodic surface mean? So if we sort of draw this, and this graph is going to be extremely horrible, and that's why we're eventually going to use some software like MatLab or Mathematica or something like that. So let's actually graph x and y here. So f is exponential in the y direction, and f is periodic in the x direction. So how do we sort of draw that? So let's draw our exponential curves. For example, this is our other curve. So for example, that is 0, 0, and 1, right? So that's the first exponential curve. And then you're going to have a bunch of parallel curves that are, some are going to be slightly above this and some are going to be slightly below this, right? But let's just draw a bunch of exponential curves that are sort of going upwards, right? So they're, at least in some sense, bounded parallel exponential functions. And then along the x direction, keep in mind this is a periodic function in the x direction. So if these are, let's say, in the same exact plane, then you should be passing through those points. So you should have a wavy surface along this type of thing, right? And that is going to be your different, that's going to be your surface, right? So when those green curves sort of dip down, that's where sort of the orange curves are also slightly decreased. Now let's consider this particular example, which is given by e to the minus x squared plus y squared. Just for terminology purposes, every time you see a function that is like an exponential to some quadratic polynomial function in the exponent, and the leading coefficient of that quadratic is an exponential negative value, usually this is going to be referred to as a Gaussian curve, or Gaussian surface if we're in or a Gaussian hypersurface, I guess, if you're in higher dimensions. And the reason we call this a Gaussian hypersurface is because it follows what we call a Gaussian distribution. And you may be familiar with this in the two-dimensional world. This is the curve of y is equal to e to the minus x squared. And if you very much raise that to the power of minus 1/2 x squared, that just sort of stretches it out in one direction. And if we divide that by, for example, the square root of 2 pi, one can show that the integral under that curve is actually going to be equal to 1, right? Which is a probability density function. But nonetheless, every curve that has, for example, a quadratic exponent with a negative coefficient, and then that's the exponent of an exponential, you're always going to get some bell-shaped looking curve, right? Either in 2D, 3D, or even higher. Now, of course, obviously, we do have a bit of symmetry here in the two-dimensional case, and we're also going to have some symmetry in the higher dimensional case. And once we start actually sketching this out, you actually see where that symmetry is going to be located. So what I want to do is I want to pick some values z and sort of see what values of x and y sort of make that equation true. So what do I mean by that? So let's, for example, choose z is equal to 1. So we want to solve the equation 1 is equal to e to the minus x squared plus y squared and find all values x, y that make this true. So if we take the natural log of both sides of this equation, that's going to give us the natural log of 1, which is 0, is equal to minus x squared plus y squared. And if we negate both sides, we're just going to get x squared plus y squared is equal to 0. So we already know that if x is a real number, and let's assume that it is, then x and y, when you square it individually and then add them together, that term is always going to be greater than or equal to 0. So the only solution to this particular equation is the particular point xy is equal to 0, 0. So that means what? That means the point 0, 0, 1 lies on the surface of this Gaussian curve, right? So that is very, very important. Also, what does that mean? So that also means a bit of other things. So let's actually investigate that. So let's assume that z is equal to some particular value of z, but in particular a negative value. And let's also include 0 in that equation as well. So if we solve this equation, what are we going to get? So we're going to have that z particular value. So we're actually looking at a set of values at one time. That's going to be equal to e to the minus x squared plus y squared. And then we're going to take the natural log of both sides of this equation. So once we take the natural log, we're going to have the natural log of those sets of values, and that's going to be equal to minus x squared plus y squared. Now keep in mind we're assuming that zp is less than or equal to 0, and keep in mind that the domain of the natural log of x function is the interval 0 to infinity. Otherwise it's undefined, right? And since we're assuming that zp is in the complement of the domain of the natural log, that means there is no solution. So that means xy does not belong to the cross product of r and r. Right? So that means there's no solution that makes this true. So therefore, since there's no xy that satisfy this particular constraint, that means that the surface is always greater than 0 for all points x and y in the domain of f. Right? And that's just a fancy way of saying that f is always above the xy plane. Okay, so we've looked at, for example, zp is equal to 1. We've looked at zp is less than or equal to 0. One can also look at, for example, between 0 and 1. We can also look at zp greater than or equal to 1. So let's start with the greater than or equal to 1 scenario. So if z is a particular value greater than or equal to 1, then we're going to have, again, zp is equal to e to the minus x squared plus y squared. And that's going to give us what? Actually, we don't need to consider equal to 1. We already considered that. So we're going to have the natural log of zp is equal to minus x squared plus y squared. The natural log of zp, if zp is greater than 1, is going to be greater than 0. So that means when we negate that, we're going to have that x squared plus y squared is less than 0. But we know that that is greater than or equal to 0, therefore that's not possible either. Right? So that means the surface is bounded above by the plane parallel to xy plane and passes through, combining with some other information we've already found, the point 0, 0, and 1. So we have the xy plane and the xy plane shifted up 1 unit. So the Gaussian curve is always in between, or sort of sandwiched in between, these two planes. So all the values of x and y are always in between 0 and 1. And let's actually look at all of those values. So let's assume that zp is in between 0 and 1. That means the natural log of these numbers is going to be in the interval minus infinity to 0, right? So if that's the case, what does that mean in terms of the graph of the surface? So if we go back to the equation that we're analyzing, so remember that the natural log of zp is going to be equal to negative x squared plus y squared. And if ZP is between 0 and 1, that's a negative. Once we negate that, that becomes a positive. That means x squared plus y squared is going to be greater than 0, which is infinitely many different types of surfaces in 2D, right? So let's assume that the value for which x squared plus y squared takes is equal to some number, let's call it r squared. And we should know that the graph of these types of surfaces are actually circles. So that means if we sort of take a plane that is parallel to the xy plane and the xy plane shifted up by 1 and sort of cut that surface, the cross section of that surface with that plane is just going to be a circle, right? So let's actually look at that type of picture. And this is what we're going to call a contour map or a contour a representation of our surface. So if we look at, for example, this x and this y, and we're going to see pretty much what values exist when we take different values of z. So when z is equal to 0, then we only have that particular point, which corresponds to 0, 0, and 1. Right? Now, when we sort of decrease that plane, right, and let's actually look at the three-dimensional representation of this, right? So we have a bunch of bell curves, so a bell curve in that direction, a bell curve in that direction, and we're going to have a bunch of cross-sectional circles for that. So if you sort of look at this horrible drawing in real life, it's actually going to look like a mountain, right? Because we're going to have some hills over there and some hills over there. So it's like a mountain. Horrible sketch of a mountain, but nonetheless a mountain. So for example, if we look at a cross section of this, right? So this red point that I have drawn here is just the intersection of that plane with that point. So if we drop this down to, for example, that value, notice that we're going to be crossing that at 2 points in a particular projection. And if we sort of rotate this due to symmetry, we're also going to have that. So for example, that's the graph, for example, of z is equal to 0. I don't know, 9. And that's going to get a little bit wider the closer and closer we get down to, for example, 0. So that's like 0.05. And of course, we have a couple other cross sections in here that we could sketch for different values of z. And that's what we usually refer to as the contour map. Right? So definitely hard to sketch, but generally you should be able to get a feel of what you're looking at from the contour surface. And we'll of course go to software and actually look at some accurate drawings of contour surfaces and real surfaces that are computer generated in just a moment. This next surface that I actually want to get into before we get into the computer-generated models for contour surfaces and the surfaces themselves is one that is of the structure x squared minus y squared. So if we sort of choose some values for x and y, what type of surface will we get? So for example, if we choose y to be equal to 0, we're going to have the curve z is equal to x squared, which we know is going to be a parabola, right? So if that's x and this is the z-axis, then that is going to be our graph. And if we choose, for example, x is equal to 0, then we're going to have the surface z is equal to minus y squared. So if this is the y-axis and this is again the z-axis, then our u is going to be downwards, right? Now keep in mind, these two u's are not facing in the same exact direction. One is actually rotated to the other 90 degrees. So if we want to represent this in 3D, how are we going to do it? So let's do our x-axis that way, let's do our y-axis that way. And how you draw these axes definitely doesn't matter, but there are some conventions that we'll get into later that sort of dictate that for us. Right. So based upon this particular sketch, if z is equal to y squared along y is equal to 0, that's going to be this particular curve here, right? Now, if we focus on the other direction, that's going to be this particular surface there, right? So that's sort of going into the board, right? And there is a commonality point in particular, 0, 0, right? So the bottom of the green is equal to the top of the blue, and they meet at that little red point there. Now, if you sort of follow these blue curves up, you actually are going to get a very interesting surface. Right? So those blue curves are sort of wrapping around, or the tops of all those little blue parabolas are touching that green parabola. Now notice if we look at this from the perspective of green, then that is a local minimum with respect to green. But if you look at it from the y perspective, that's actually a local maximum. So if it's a local maximum, let's actually write that down because that's actually pretty interesting. So 0, 0, 0 is a local minimum with respect to the xz plane, and 0, 0, 0 is a local maximum with respect to the yz plane. So every time you have, a point that's a maximum in one direction and a minimum in the other direction, this is usually what we refer to as a saddle point. It's not a formal definition of what a saddle point is. We'll get into the formal definitions later when we start talking about derivatives in higher dimensions. But those different types of surfaces definitely are super common when we're actually going to study higher dimensional surfaces in calculus. So I just wanted to introduce those things to you. Now what we're going to do is we're going to go to MATLAB and actually go ahead and graph these surfaces so we can get away from my ugly sketches and also learn how we can construct contour plots for these surfaces so that, for example, we can represent them in two-dimensional space and still be able to interpret those three-dimensional surfaces and possibly even approximate some maximums and minimums of those 3D surfaces. So now what we're going to do is we're going to go ahead and see if we can generate these 3D surfaces in MATLAB and also generate some contour plots as well. So the very first thing I want to do is create the functions that I want to graph in 3D. So to do that, what I'm going to do is I'm going to create a inline function, and it's going to be of two variables, x and y, and you can do that via this type of code. So I want to do the sine x plus e to the y, but I would just want to introduce a little bit more fluctuation, make the period a little bit more smaller so we actually see the ripples on a shorter domain. So the function that I want to do is going to be 3 times the sine of, let's do 3x, and then plus e to the power of y. So those are going to be my two functions. So this is the surface that I'm actually going to be going ahead and drawing for us. Now what I want to do is I want to create a mesh grid of the domain for which I want to plot on. So what do I mean by that? So for example, the x domain that I want to plot on, I want to do, for example, from -4 to 4 in spaces of size 1. So that's going to be the vector for my x domain, and I want my y domain to be the same, for example, from -4 to 4 in spacings of size 4. If you know anything about vectors, that's pretty much what we're looking at here. We have xx, that's a vector in the x direction, yy is going to be a vector in the y direction, and what we're going to do is we're going to pretty much take the cross product of these two vectors and pretty much have a plane with a bunch of little points that we're going to sort of use as our domain for our three-dimensional function. All right, so how are we going to do that? So to create the cross product between xx and yy, what we're going to do is we're going to do xy, so that's going to be our mesh grid, and this is going to be mesh grid of xx and yy. Right? So once we have our mesh grid constructed, then we can actually graph our surface. So in order to graph our surface, the first thing you should do is, of course, specify the figure that you want to open, and then what we're going to do is we're going to serve x, y, and then z, which is going to be our f function. So we're going to do f, x, and y, and that should construct the surface for which we're interested in analyzing. So once we actually give that a run, we actually get our beautiful surface, which is given to be here. Right, so of course we have all our little rotational tools up here if you're using the most recent version of MATLAB, but that is how we have or generate surfaces in MATLAB. And notice that we have an exponential increase in one direction and we have a periodic pattern in the other direction. So that is our exponentially periodic function for which we were talking about a little bit earlier. Now let's see if we can generate the Gaussian service that we studied as well. So what I want to do is I just want to delete or change this particular function. Let's just graph on the same exact interval as before. And we're going to do e to the power minus x squared plus y squared. Let's put that in parentheses. So x squared plus y squared. Now, keep in mind, x and y are not numbers here. X and y are going to be vectors. Every time you're dealing with division and exponents and multiplication, you should always be using dot operations when you're in MATLAB. So that's going to be element-wise squaring, because if you have a column vector and a column vector, you cannot square them because their inner dimensions don't agree. You can't do a 3 by 1 times a 3 by 1 because 1 does not equal 3. Right? So just to be safe, you can technically always do dot operations. It might be an overkill in terms of coding, but usually you won't have as many errors as not putting them there, just in case you forget. So if that is our Gaussian surface, for which we're interested in plotting, we just give that a run, and that is going to be our little bell-shaped curve, which is so much more better than the sketch that I had before, right? But that is our little mountain, which is a Gaussian surface in one direction and a Gaussian surface in the other direction. Now let's give it a go in terms of graphing the saddle curve that we had before, or the curve that had a saddle point, which was going to be equal to x squared minus y squared. So that is going to be our saddle surface, I guess you could say. So if we give that a run, that's our saddle surface, right? So notice that it's a minimum with respect to that direction, but if we look at it from this direction, it's also a minimum, or a maximum rather, and that little saddle point's sort of chilling there at 0, 0, and 0. The next thing I want to do is discuss how to construct contour plots or contour curves in the MATLAB programming language, which is sometimes a little bit more easier to interpret in the two-dimensional world. Let's assume that we actually want to look at the contour plot for this saddle surface given here. So to do that, we're going to plot it in a different figure because maybe we want the surface to be in a figure and the contour plot to be in another figure, right? And in order to combine them into the same plot, we'll get into them probably a little bit later, but now let's just keep them separate. So what I want to do is I want to just use the function contour and then do x, y, and then z, which is again going to be f of x, y. Okay, so when we run this particular curve, what we're going to have is we're going to have a plot that looks as so. In case you want to do a color bar to sort of see the level values for which we're looking at, you can just do, for example, color bar in the command window, or you can actually do color bar just in case you don't always want to run that code in your compile time. Right? So everywhere you see a dark blue value, that's going to be a negative number, and everywhere where you see a yellow value, that's going to be a positive number. So if you sort of look at this and what it sort of represents, these yellow values is the largest z value that you obtain in this particular surface, and they're located on the right and the left, and this is the x-axis and the y-axis, and of course you can label them if you want to. And everywhere where, you know, like for example down here and up there, that's where these sort of values dip down, right? And notice that we have that little intersection point 0. Notice that it's higher to the left to the right of it, and it's also lower to the left and to the right of it if you rotate 90 degrees. That means you can justify that that point right there would be a saddle point from that particular perspective. Now you can also display, for example, several different levels. For example, we have maybe 1, 2, 3, 4, 5, 6, 7 different levels in this particular picture. You can actually increase the number of levels if you really want to with very minimal change of code. So the next number, if you were to input it, for example, would be 10. That's actually going to be the number of levels that you actually indicate on your particular contour plot, which notice that the more or the higher value the number of levels you have, that's how many sort of z values you plot in that particular code. So for example, if I include this to 100, then you're going to be looking at let's say 100 different planes that are sort of cutting through the surface for which we're analyzing here. And this, it's a little bit more easier to see that that is going to be indeed a saddle point just by the trajectories of each of these level curves, which is actually pretty interesting. So what I actually just want to close with today is maybe just another surface just to sort of get some insight, just to make it a little bit more fun. Let's do, for example, sine x plus cosine of y, and let's see what kind of fun surfaces we can make with this. So if we run that, notice that this is the very interesting surface that we get from that particular curve, right? So what do we have going on here? So notice that if we look at this point right here, which is approximately like 1.5 or 0, 1.5, and the z values are marked in this particular color, notice that the values go from really bright and to really dark as you move to the left, up, right, or down. So you can see that this point is going to be a maximum, and that's actually corresponding to this point right here, that big maximum value there. And these different types of shapes, these star-looking things, that should look familiar because that is actually the shape of a saddle point, right? So for example, this point right here is corresponding to this saddle point located right there. That saddle point right there is located at that point right there, right? And what is this point right here? So that's the local minimum located back here in the bottom corner, and this little circle down here corresponds to that value located right there. So notice that technically I can hide the surface plot, and you can actually interpret what the 3D surface actually looks like just from the contour plot or contour curves for that 3D surface, which is why contour curves and level curves are so very useful for interpreting higher dimensional surfaces, right? So those are the basics of interpreting 3D and also higher dimensional surfaces using level curves, contour curves, and a couple little things in MATLAB to help you visualize this, just in case your drawings are as bad as mine. So I hope you enjoyed, and I'll see you in the next video. Take care.